let's take a look at this question about optical fibers, which are incredibly useful. It says that the glass core of this optical fiber has an index of refraction of 1.60. The index of refraction of the cladding, which is the outer part of the fiber, is 1.48. So it asks us what the maximum angle the light ray can make with the wall of the core is if it is to remain inside the fiber. Remember, for this whole device to be useful, the light has to be contained within that core so it can transmit information down the wire. If it escapes, the whole thing doesn't work very well. So this relies on the idea of total internal reflection. So let's just remind ourselves what the critical angle is. So the critical angle is where we have an angle of refraction is equal to 90 degrees. Because beyond this point, we're going to have total internal reflection. And you can derive this by looking at Snell's law, where we have n1 sine theta 1 is equal to n2 sine theta 2. So we're going from the one material into the second. And so we find the critical angle by saying, well, this is going to be our critical angle at which we're going to have a refracted angle that's equal to sine 90. And what is sine of 90? It's 1. So then we can isolate for the critical angle. And find that the critical angle is equal to inverse sine and the ratio of the two indices of refraction. Okay, so given that, let's apply this idea to our problem. I'm just going to move this up just a little bit to give us a bit of room. Okay. So in our problem, we have some light ray that's going to be, and I'm going to, maybe I'll draw a normal for reference. And we'll do that in gray and maybe dotted. Okay, so let's just draw some reference here. That looks pretty good. And then we're going to have a light ray example where we have some light ray coming in, and we want to know what the critical angle is. So that this stays inside the core. This is what we absolutely must have for a fiber optic cable to work. And so to zoom in here a little bit, what we want to find is this angle here. And then we know this angle as well, because that's the angle it can make with respect to the boundary here of the core, which is the question. So it's kind of interesting to note that we got to very carefully interpret this. It's asking for the maximum angle the light ray makes with the wall of the core. Now that's not the angle that we normally use. That's not usually the reference point that we use for these refraction questions. Usually we're taking it with respect to the normal to that surface. Okay, so just to make a note of this, I think it's very important in terms of applying the critical angle. So we can have total internal reflection the end of the core is larger than the end of the cladding. And so we know from the question that the end of the core is 1.6, so it's a denser medium. So this only works when you are containing the light ray within the denser medium. Okay, so what's the maximum angle here? Well, let's first work out what the critical angle is. The critical angle is inverse sine of N2, N1. Well, the second material is the N cladding. Zoom in here to write more clearly. N cladding over, make this a bit bigger, and core. Okay, so then we can say, well, my critical angle is sine and cladding was 1.48, I think. Yeah, and then it was 1.6 for the core. And so the critical angle works out to be 67.7 degrees. Good enough. Okay, but that is not what we're asked for. That's the critical angle, but we're actually looking for that what I've denoted as this phi term. Okay, so that means the max angle light can make with the wall of the core. I'll just note that I denote that as phi, and remain inside the fiber is 90 degrees minus 67.7 degrees is equal to 23.3 degrees. And there we go. And this is a nice little review of both total internal reflection as well as looking at how optical fibers actually work. And that's it.